and here we go. I'm so excited I'm going to record it that Joe is going to give us a very interesting talk on resilient math problems. I'll turn it over to you.
Yeah, thanks, Joe. All right, so hello everyone. Well, first of all, right, we made spring break, so this talk is very low level, kind of more of a fun talk. So really, just sit back, but get some pizza. Most of you already have. Get a drink and just enjoy. This talk. If you ever have any examples of your own that you think of either during it or afterwards, just come talk to me and share them with me. I want to kind of build a database of these problems. These resilient math problems, but this means that they can resist common student errors, right? So creating a negative sign or adding fractions incorrectly, and so on and so forth. But let's go ahead and begin with just a couple of fun problems. So these aren't very hard problems, but there's kind of more fun ones that are kind of unique. If you've seen the solution, I guess one of them was actually given to me by Jim, that don't ruin it for everyone else, let them solve it. So first is, let's see, so right here, just some fun with some fractions. You start with 16 over 64, and you're asked to reduce it. Of course, what's the trick? Maybe you already know. Well, there's a 6 up top, 2 down below. I get 1/4. All right? And actually, we get one more.
Also, and you should probably make really clear that this is a joke along the way. Otherwise, YouTube, there's going to be this viral video about the math crisis. Thinks that's how you cancel.
26 over 65. Again, 6 up top, down below. Get 2/5. It works. One more fun one involving fractions. This is probably my favorite of these three. So 9/2 minus 25/10. Anyone ever seen this one? We all know how to subtract fractions. 9 minus 25, 2 minus 10. I'm going to get, what do I get here? Negative 16 over negative 8. And there we go. All right. This subtract them right across, we get the right answer. Okay, so again, there's three kind of fun ones. One that's a little bit more serious. It involves a little bit of calculus, right? It involves an integral. Let's look at the integral of 1 over x. 1 x, and we will use, well, let's split up our denominator. This is the integral of 1 over x, right? Plus 1 over 1. Dx. Okay. We keep working with this. So that first piece, I'll just write both of them as with a dx, right? But 1 over x dx, we have plus integral of 1 over 1 dx. We know what this is, right? 1 over x, the natural log of x, plus, well, if 1 over x is the natural log of x, then the natural log of 1 over 1 is, sorry, 1 over 1 is the natural log of 1. And as we know, the log is linear. And of course, we won't forget the plus c at the end, just so we get the total correct answer there. Right, so again, just following the pattern, right? 1 over x, natural log, 1 over 1, natural log of 1. And we are good. Flawless. Yes, perfect, right? No problem there at all. You're right, Jen. This is going to get the internet in there. I'll be ruined. So this next one was given me by Jim himself. So Jim, you're not allowed to spoil it, but I did ramp it up a little bit. What do we have? We're given that n equals 2, and we have that that x equals our nice inverse trig function, the arc cosine of 3/5. And what do we want to find? Well, of course, we want to find sine of x. And we know how to do this. This equals 6. Does anybody see how we did that?
Mhm.
What did we do?
Sorry, you just canceled it.
Right? And it actually is, right? Because I mean we can show this one, right? So the arc cosine. There's my angle X. I have a nice 3, 4, 5 triangle here. Cosine's the adjacent. So what do I actually get? So sine of X over n. Well, n is 2/15. What do I get? Well, sine is the SO of SOHCAHTOA, so opposite over hypotenuse. So I get 4/5 divided by 2/15 or times 15/2. I get 3, I get 2, 6. Right? So again, if at the end of this, you have one of these problems, let me know, and I'm going to add it to my list. So let's keep rolling. We haven't gone to my favorite one yet. I'm storing that one. So how about simplify? X squared minus y squared, x minus y. Any thoughts?
X minus y.
Well, almost. X here, X there, Y here, Y there. Well, what's left? 2 negatives made positive. We're there. We have simplified our expression all the way.
Negative running. Yeah, I really didn't see that.
Yeah. This next one, I will work out both ways, but I will do the wrong way first because that's more entertaining. Just to show you that it actually does work. All right, so what are we're solving? We have another equation. Negative 5x plus 35 plus 7 equals x. I need to isolate my square root, so I can square both sides and solve for what x is. So I'll do just that. So nothing yet, right? Square both sides. We know how to square a square root, this goes away. We know how to square this. Right? Both of my terms get squared. And now we just solve. All right, what do we have? Let's move everything to the left-hand side. So I have a, to the right-hand side. So I have a positive x squared, but of course I'll write it on the left. So I have x squared plus 5x. And then minus 8 and 4 equals 0. And this does factor nicely. That's x plus 12 and x minus 7. And so I get x equals 7 and x equals -12. Now you have to plug it back into the, squaring it, we added some solutions. So we have to check, like plug it back in and check. So I plug in 7, well, right, I think I do this one by hand, right? Plug in 7, I get -35 plus 35. So I get 0 plus 7 equals 7, right? So keeper, plug in -12. Negative 3 squared root of -5 times -12. 6 5 plus 7 equals 12. This is positive, this is positive, this is negative, right? No. So we get the answer, the only answer, x equals -7. Now, of course, if we did this correctly, we have to expand this out all the way. And so instead of getting what we have right here, we eventually get, so jumping down at negative 5x plus 35 equals, and we get x squared minus 14x, and then plus 45. But you will see what we still get. So what do I have? This look like. Oh, yes. I'm going to get x squared. It's 9x. Bring it over here. So it's that plus. Which is so that's minus 2. And so we get two solutions, 7 and 2. You'll find that this one is correct and this one is wrong. So again, you get the right answer.
Yeah, and
Right. So
yeah,
you only
it
get the one.
actually is correct if you take the other sign on the radical, right? So in other words, if you take the negative square root in your original equation.
Yes. Yeah. Because this, yeah, squaring and negative take it away. Yep.
Yeah, but that's 12, right? That's
Oh, so this is a quick little fun one. You've probably seen it before.
that's related to the sum of long.
So I've already made a comment about the log being linear. All right, that won't work anywhere else. All right. All right, so I'm reaching the end of my examples. I have 2 left, but then I have some questions for you all, or some homework, or more so, I wanted to see if any of you know the answer. First, what's that? Oh, okay. I was gonna say first, I want to give my favorite example that I have here of finding the derivative of 1 over x. This is my favorite one. Have you seen this one? Or, yeah. What do I have? I have a d over d. I have an x here, that gives me x squared. What remains? Well, I have this line. But there we go. Done just like that. So this one right here is my favorite. And to wrap it up, this problem was came about because of a class I'm teaching. I had a student, and I thought, like, oh no, you can't do it that way. And they almost got the right answer, and they were only off by a negative. And I was thinking, why are they so close to the right answer when they made a very critical error along the way? And so I investigated it. And so we'll do one example of it, and then I kind of want to generalize it. And then I also want to see, now I get to ask you all a question. So given g of x, which is 3x minus 4. We would like to find all solutions to f of x equals g of x. Not too hard. I can just set them equal to each other. We all know how to solve a quadratic. I move everything to x to the one side. Let me bring out the real estate here. Let me bring it up here. We move everything with x to the one side. Then I look on the left-hand side, they both have an x. Factor out. And we know when I have a product that equals a number, each of the terms must equal the number. X must equal -4, and negative x minus 3 must also equal -4. And here I can add 3, so I get negative x equals -1, or x. Take both of those, plug it back in, you will get the right answer. This was the most frustrating one to me. And so I did want to investigate it, and I wanted to say, how many times does this occur? And so I went to, if you ever want to make up a problem where this happens, the students can get away with this trick, which I guess I don't advise. Then you can do the following. And there's kind of two ways of thinking about it, but one's more, I found one more pleasing in the end, so I'll do that method. So if you want to manufacture your own quadratic, right, that can be solved like this. So what do we have? So we want to consider a quadratic has this form here. And I'd really like to be able to do this trick where I can have ax squared plus x equals -c. And I get that. I get the solutions x equals -c. And I'll also get that ax plus b equals -c. But the restraint that we have is when x equals -c, right, we must have that ax plus b equals 1. Then multiply by -c. And also when ax plus b equals -c, then x equals 1. Right? So we need that to happen in order for this solution to work in general. And so we can work with these restraints. So when x equals -c, then this equals 1. Well, I can just take, that's just saying, well, if x equals -c, this is -ac plus b equals 1, right? Just going out there, which is the same as b equals 1 plus ac. And then down here, right, when ax plus b equals c, well, then x must equal 1. And so I get that. Okay. So we take b equals 1 plus ac, and we substitute it in right here. So a plus 1 c. Here I'll move my 1 to the right hand side. I'll be left with a plus ac, -c minus 1 plus a plus c -c minus 1. And last but not least, I can fit it. A equals -c minus 1 over 1 plus c. And of course, these two are only factor -1 away. And so in order for this to happen, you must have your leading term as -1. In fact, that's enough. So once I know this, I know that b equals 1 minus c. And so you can get the form -x squared plus 1 minus c x plus c equals 0. If it has this form, you can always solve it that way. Right? You always get the roots that you want. So pick any that you would like. In my case, I think I picked c equals 4. Or yeah, I think that would work for the solution. Yeah. And I got both of the solutions. So that'd be an infinite family. All right, well, that is all that I have. Another.
That's interesting that wherever you saw this problem, they were just unfortunate. They picked this so that it.
Well, what goes wrong is, so this has the roots that we want and this method, but if you multiply by -1, you don't change the roots, but you can't do that anymore. And that's what my students say, and they're off by a negative. So if you do x squared plus c minus 1 minus c equals 0, which the roots are exactly the same because I just multiply both sides by -1, this doesn't work anymore. Because on the right-hand side, right, the negative doesn't change anything, but when we have it in this form, right, multiplying -1 affects both sides. And only one of these two factors. So one of them will be off by negative. And that's what happened.
Did you investigate what happens when C is -1? Right. So when the formula for A becomes singular.
When C is -1?
Yeah, so if you look at the bottom, like right to your left a little bit. So you got that formula for A being -1 when C is -1. So
no, I never.
Because I mean, what will happen is that that's actually a perfect square in that case.
No. Yes, +2. So what happens here? I'm not sure, right? Let's find out. Yeah, -x plus 2 is 1. 1. Okay, 2, 1. Yep.
Yeah,
Right.
so got like the double root. So
Yeah. I think that's good. All right, so I do have, I'm curious if any of you know the answer, and if not, then I guess it's homework over spring break. So I had one example of where you could distribute the exponent through, right? You distribute the exponent, you got the right answer at the end. I really wanted to come up with an example where you could split the square root and get the same answer at the end, but I could not find, I couldn't find the right problem, but I had the idea for it, and if it's too hard, then so be it. But this is the one that I mentioned to you a moment ago. So we have half of a circle. 1 minus square root of 1 minus x squared. And if you could think about distributing the square root, right, I can look at 1 minus x, which is a line. Right, the total area from -1 to 1 underneath the circle is well, pi r squared, r is 1, so let me just write it. So the integral -1 to 1 of the square root of 1 minus x squared x half the area of the circle, and also the integral -1 to 1 of my line 1 minus x. Well, it's a triangle with height 2, base 2, so it actually has area 2. So this area is larger than this area from -1 to 1. However, 1 to 0, clearly, right, the area underneath half of the circle is larger. And so at some point, the area underneath the line and the area underneath the circle are the same. I'd like to find out where does that happen, right? So what x value here makes the two areas equal together? So if I change this to maybe x, or not an x, but a to b, right? An a, right? What's the value of a such that these two areas are equal to each other? So any of you know, tell me. I'll write it down. But otherwise, thank you for coming to my short talk. And if there are any questions or examples that you have, I would love to hear them.
Yeah, we can work that out actually.
Yeah, that's what I was.
Well, yeah, I tried, but the integral is.
So there is the stuff you were trying out with, like 16 over 6.
Yeah.
I wonder if you can generalize that by talking about it in terms of different bases. Because like maybe I write it out.
Yeah. Oh, please, yeah, go ahead.
So you got like 16 is 1 times 10 plus.
Here, write a little bit probably into the like you know, can a little bit.
1 times 10 plus 6 over 6 times 10 plus 4. And then you have that 6 times 10 plus 4 times 4 is equal to
Oh, so 16. Or would you write it as?
no, let me do it this way. Basically, this is the general base. So, how do you generalize this? Tends at the same place.
So you're trying to find a general form where you can cancel the 6's.
Yes.
And you get the right answer.
Yes. And so the idea is that you want something in 1 times 10 plus in 2 times k is equal to, we're going to do the n2 here plus I'm terrible at math. Right. Then you find more solutions. In the range from 0 to 9.
Yeah, I guess I'm gonna.
Hi, mate.
So like for your problem, like a closed form solution, right?
That would be ideal. I know it's gonna be hideous. Because to do that integral, you did your tricks up.
Yeah, so I think that my guess is just looking at this is, I mean, we can find that a numerically, right? But
Yeah,
I think that
it's between the like
because there's an algebraic equation. It's almost algebraic in A, except it's got an inverse sine term in it. And so then so you're in trouble there.
Yeah.
Well, let's thank Joe. So you want to see my example? So this is the most hideous thing I ever did to a student.
Yeah. Oh yeah.
So first we got to do a problem first. So you guys can help me with this. This is a problem that I put on one of my calculus exams back in the day when I was in North Dakota State. And the problem was I drew him a picture like this. I gave him this particular parabola. So I set this up so it's this parabola is inverted because A is positive, and it's got intercepts here. Pretty easy to pick that out. And so now that you know, since A is positive, it reaches its maximum in the middle, you know. So not too bad. That wasn't really the sort of focus of the problem. I drew a line here. And to appreciate this, I've got to work through it. So A is fixed, and the question is find M such that the region under parabola is cut in half. Right, so what value do you need to cut this thing exactly in half? And I apologize to you, Alec, because you're going to hear this little joke later. When we talk about Galois theory. So how do you do this, right? Well, and of course, because this is kind of a tough problem in the sense of going through it to get the example. Of course, a nice guy, and it's like pretty much the lion's share of the points where can they set this up right? And so probably the easiest thing to do is to find the intercept here, right? And so we do this. Right. And of course, one solution to this is x equals 0, which makes sense with my picture, right? So good for us. Or m over a is 1 minus x. And so x is equal to 1 minus m over a. And so there we go. Right. And we can also find the total area under the parabola and see how we can adjust this to make it be half of it. The total area is the integral from 0 to 1. I'll go ahead and multiply that out. It'll be easier for me to integrate that way, right? Which is a x squared over 2 minus a x cubed over 3, 1 to 0. So whatever this is a over 6, isn't it? Right. And so what we need, probably, well, okay, so what do we need? What's the easiest way to finish this off, do you think?
Do the integral of ax times 1 minus x minus mx.
So I've got two regions here. I've got two regions to pick from, upper and lower, right? And I want to make whichever one I pick, I want it to make half of this. So I want it to make over 12. Right? Which region would you pick?
Top one.
Top one. What's better about the top one?
You can do it with a single one.
That's right. You don't have to do more than one integral here, right? Because the top is always the parabola, and the bottom is always the line. Whereas here, the line is the top for a while, and the parabola is the top for a while, which is obnoxious. So what we need is we need a over 12 to equal the integral from 12. Let's do top minus bottom. Ax minus ax squared. There's your top function minus mx dx. And my limits need to go from 0 to alpha, where alpha is, because I don't want to write this crap every time, right? So I'll shove that in later, right? That's one of the best things that engineers can learn in like a calculus class is symbols are much easier than concrete numbers. So what do we get here? Seems pretty easy. This is a x squared over 2 minus a x cubed over 3 minus m x squared over 2. Right? Now the price I pay is I don't have a, well, no, actually this is also better because I have a 0 here, right? So this is equal to a, let's say 1/2 a alpha squared minus 1/3 a alpha cubed minus 1/2 m alpha squared. Right. So this is, there's an alpha squared here. 1/2 a minus 1/3 a alpha minus 1/2 m. And what are we trying to find? Well, we're trying to find m, right? So in particular, to find m, we can find alpha. Notice that alpha is this, which is also equal to a minus m over a. So let's see. Notice, by the way, that we're done with the calculus, right? I mean, from here on out, it's just alpha, right? Trying to figure all this out. So this is going to be a over 12 is alpha squared. So let's put that down as a minus m over a squared, right? And this is 1/2 a and let's see, that's 1/3 a times whatever it was, a minus m over a. Right? You guys should jump on me if you catch me doing something wrong. And this is 1/2 m. Right? And actually something rather miraculous occurs here because this is 1/2 a minus m, checking these two off, right? And the a's cancel. Right? You can't beat that with a stick because what you have here is 1/6 a minus m. So now we have a much simpler equation. And this is a over 12 is equal to, well, I'll write this out in one step here, a minus m squared over a squared times 1/6 a minus m. Right? So let's kind of, I mean, what we got to do is solve for m, and this looks awful. However, I'm going to bring the 6 over here and this a squared over here. So I'm going to take the 6 and a squared, the denominator over here. And so I get 1/2 a cubed is a minus m cubed. Agreed? And all of a sudden, this looks doable. Take the cube root. A equals a minus m. And now you can solve for m. Because you get m is equal to a times 1 minus 1 over the cube root 2. And so m equals, well, there it is. You already got it. Yeah. So whatever a is, notice it's scaled by a, and this is kind of this factor. And of course, this makes sense because 1 over the cube root of 2 is something that's a little less than 1. So this will be about like the picture said, right? Okay, that's my little problem that I gave, right? It was sort of a centerpiece problem for the calculus test. Most people got 7 or 8 out of 10 just by getting it set up. Very few people, like maybe a handful in my class, got all the way to the end. And of them, I was very proud, right? The algebra is the worst part of this problem, right?
So when you teach a large lecture class, grandparents die all the time, right? And so there's always 5 or 6 people. Oh, you know, my grandfather got the measles, whatever. And so I never turned people away. And so I was like, yeah, come on in. Well, I gave a makeup test, and there was this one guy that didn't even show up for the makeup test. And then he didn't show up again. And for his makeup test, I had made up pretty much the same thing. And the last problem I had to do is I had to replace that one on his makeup test. Now, I'm thinking, I can't make it easier, right? That's not fair to everybody else. But how do I capture this, you know, sort of thing? So he finally showed up at my office, and I hadn't finished the problem because he had missed the last 3 times. He shows up at my office. He goes, "I'm ready to fix this." I said, "Okay, go sit down, and I'll make it up." And so I closed the door, and I was like, "Oh, what am I going to do about this problem?" So I was trying to, maybe I should come up with something else. I said, "Oh, I know what to do." Same problem, same picture, but this time rotate it around the x-axis and tell me the value of the slope that cuts the volume in half. Same idea, right? So, right, and instead of finding the area, just spin this around and cut the volume in half. Well, I made up the test because he was there and I gave him the test, and I went back in my office, and I'm not going to be able to give you the exact thing. But I'll have to work this out because I've got my own curiosity here. But I sat down and I worked this out. It was unbelievable. I was so proud of myself. I got it reduced to, if I recall correctly, it was a 10th degree polynomial with Galois group S5. So it's impossible to solve by radicals. And I was like, yeah, he gets full credit if he sets it up right. Of course, I got the test back and he didn't even do it. So I worried a lot for nothing.
Well, couldn't you cheat and say n equals 0? Like if you revolve around the x-axis, or is that kind of cheating?
No, what I mean is when you spin this around, you'll get this kind of you know, football looking thing, if you will, right? I mean, when you spin it around.
Yeah, almost like a.
And so what I want to do here is, right. So if you do this, then what that will do is, yeah, I see what you're saying. If he had made a good argument, I would have said
kind of
something
like,
about that.
you mean kind of like the area to the right and the other to the left,
Right.
where does that cut in half?
So, yeah, so imagine what this does. It spins around. Yeah, because 0 wasn't a solution actually. Yeah, because what would happen in the 0 case is the way the integral works is it would think that this piece had volume 0 and the other piece had full volume, right? So what?
Oh yeah.
Right. So when you spin it around, it looks something like this.
Yeah, it looks like a.
It looks like a UFO.
There
right?
you go. Yeah, that's good.
Sort of like that.
And
this sort of cuts it out. So this will be sort of the outer skin of the UFO and so forth. If it was 0, it would think that it's essentially pulling nothing or pulling the whole thing.
you have you're gonna have a cone on the inside, and then the frisbee cut out.
Yeah. So yeah, what you're cutting out is a cone with like a little bit of funny bottom that's curved into it, right?
It's kind of like an ellipsoid, but it's got pointy bits.
And I will give you one more anecdote. When I was a grad student, there was a kid in my calculus class who will remain nameless forevermore. But he was a bright enough guy, but he ended up he was like a DJ on the radio station that the school had, and so he was up like plenty hours, right? And so he would miss class from time to time. Smart enough guy, but anyway, so it was a Calc 2 thing, and we were looking at parametric equations. And so if you draw something parametrically like this, there's ways that you can figure out the area under the curve, right? Just by almost treating it like Cartesian. And then if the parameter, if it's like a theta parameter, it draws it, then there's the area enclosed by it, which is something different. And I emphasized this to my class. This was one of the days he wasn't there. And I remember telling him about it later because I was worried he was going to mix this up. But they had a problem on the exam. And it was a curve. I don't remember what the curve was, but it was like this. And it was, they were asking to find the area enclosed by the curve. Right? And so this guy made the mistake that a lot of people made a mistake. Instead of doing this, he actually did the entire white area under the curve, right? It didn't use the formula properly and did this. And so it was an 8-point problem. He got 1 out of 8 because he messed it up. You know, he just did the wrong problem. It wasn't me that graded it because this was a large, it was coordinated section, and you know, somebody else graded this problem. So he came back to my office and complained. Well, not really complained. Well, I don't understand why I only got 1 out of 8. And I looked at it and immediately saw what he did. And I said, well, because you did the wrong problem, here's what you did, blah, blah, blah. And he's like, oh, okay. All right, I get it. And he left. 2 days later, he came back and goes, yeah, you know, I still don't get it. So I said, well, no, here's what you did, and here's what was asked. And then I worked through what was asked. And I said, this is what the answer should be, blah, blah, blah. He was like, oh, okay, I get it. And then he came back 2 days later. He goes, yeah, you know, I still don't get it. Now, this time I looked very carefully at his paper. I hadn't before, but he was, I mean, his paper was smeared up. It looked like it was written in crayon. It was all, and, you know, stuff going down here and then continued on 2 pages back. It was a maze, right? And so that's why I really hadn't looked at it carefully before. But he went through all this stuff and go back to this page, go to this page and all this kind of thing. And he got the right answer. And the right answer wasn't 4. It was like the square root of 3 over 8 minus pi squared over 27 or something like that. It was a bizarro answer, and he got it right. And I was shocked. I didn't know what to make of this. So it reminded me very much of Joe's talk. I was like, let me take this home and look at it, because I thought maybe there's something I can steal here. I mean, he might have discovered something, right? And I looked at it, and after looking at it, going through his process of logic, starting with the wrong problem, that's obviously going to get you, I mean, it's clear that this area, the white area, is bigger than the other one. Starting through this, he went through and I was mess. I went and checked it. He made 6, what I would consider to be major mistakes. Things like this. I mean, he did 6 things like this. And for those of you out there watching with this YouTube video, this is not right. But he did 6 things like this. And somehow, and every time he made a mistake, the logic to the next step followed. And I was like, okay, this is wrong, but if it were right, the next step would be correct. And he got the right answer. And it was just, I had to tell him, I said, played the lottery that day, because that's what you should have done instead of playing the credit. I said, the universe has played a very cruel trick on you, because you've done 6 things and you just somehow you kind of won the lottery. And he complained, well, I got the right answer. I said, listen, I said, you wouldn't be back here complaining if the answer you got was 8. Am I correct? He goes, well, yeah, that's right. I said, your answer's no better than 8, right? It's just, this is just a very cruel trick the universe has played on you. So actually, the funny thing is then he left and he went and complained to the coordinator and the grader. And he complained for the rest of the semester until finally the coordinator had to ask his college to leave him alone. So anyway, but math can be cruel sometimes.
I wonder if you could get like a list of problems that you can, like mistakes like that you can undo by performing another mistake.
No, that sounds like something that'd be very dangerous in the wrong hands. Okay, any questions out there? Questions here? Let's thank Joe again. Yeah. Well, everyone, have a happy spring break. Be safe, have some fun, and we'll see you after the break's over.